Welcome back to my channel. I'm Brian Kafaki, and I'm excited to continue my series on Databricks and Apache Spark Performance Tuning. This is lesson 2, the low-hanging fruit video, or the easiest fix and way to get your workloads optimized kind of before you even start trying to do much. And that's by getting the resources correct right at the start. Before I jump in, I want to thank my Patreon supporters. I couldn't do this without you, so I appreciate all the support you give me. If anyone else is interested, I will leave a link in the description. Where are we going? We're going to talk about why compute resources matter, Databricks Workspace, Standard or Premium, Databricks and Apache Spark cluster architecture, and then we'll discuss the hardware underneath that architecture, which leads us into the discussion on how to optimize our cluster configuration step by step. And I want to give a special focus on shuffles and spills because those are usually the place you're going to have the biggest performance hits. And finally, we'll wrap things up. Why are we talking about this, Brian? What's going on? Why do we care about resources and whatnot, especially in the cloud, right? Well, I was surprised when I started to think about this, how really it's not that covered. At least I haven't seen a lot of good documentation about what options to select for our clusters and what the effect is on each one. I've seen it in bits and pieces, and I did find a pretty good single page which I consolidated recommending the type of nodes you should use depending on the workload. But the main reason I want to jump into this is because it's very important and not usually covered very much. Now, historically, I go way back, and the age-old thing has always been the cost versus performance. Traditionally, on the old legacy, SQL Server databases, you could always throw more hardware at the problem, get a bigger machine, add faster this and faster that, and generally that would get rid of performance problems. But of course, that's a trade-off. Lots of money versus performance. With Databricks, the idea is not to spend a ton of money as much as get the right balance. As long as you get the right sizing and types of nodes running and the right number of nodes, then you should get the best performance at the best cost. And I want to emphasize, this is the single easiest thing you can do to improve your performance. If you've got the wrong sizing, the wrong resources being allocated to your workloads, then anything else is probably not the best way to go. So get this right. I also want to emphasize that there are interdependencies between performance optimization and the compute selection resources and options and how they interact. And what do I mean by that? So for instance, if you create a cluster and it doesn't support Unity Catalog, then you will not be able to take advantage of Unity Catalog features related to performance. Similarly, as we'll see, when we get to creating a workspace, some of the things you'll need to do to improve performance require the premium workspace versus standard. So let's talk about that first. This is the screen you go to when you want to create an Azure Databricks workspace on Azure. And I want to call your attention to this particular point here. It's the pricing tier. Now, I don't know that there's a huge difference in pricing between premium or standard. And I think at this point, the general recommendation is, except for maybe certain types of workloads, maybe development or something, go with premium. It gives you role-based access controls, and that is really good for security, but there's a lot of other things it also helps you with. For instance, if you go with premium, then you get to use Unity Catalog. It requires premium. If you want to do Delta Live tables, that also requires premium. What are Delta Live tables, Brian? I will put a link in the description to my riveting Delta Live tables video, glad you asked. But Delta Live tables is really a kind of automated way to create data pipelines. And the nice thing about it is it does all kinds of cool services like tracking lineage and give you insight into it. And it has some intelligence about what you're doing. In other words, it understands what the various data assets are that you're building. As I mentioned, it's automated, so it takes care of a lot of the work for you. Now, whether it performs better or not, I'm not sure. It probably depends on what you're doing and the workloads, but it does take care of a lot of the issues of maintaining and running workloads. So it's something you want to have available in many cases. Fortunately, I had to research this, I wasn't sure, but Photon does not require the premium tier. So that's a good thing because Photon is just really good. I was trying to get bad performance and I had Photon turned on and I just couldn't. It was too smart. So I couldn't fool it into giving me bad performance, or I wanted to create a spill and it just wouldn't spill. And I didn't want to spend a fortune to add so much data to do a spill. So I'll show you a little trick I used. But good news, Photon does not require premium. And I just want to call this out. I found the links. You can get these slides. I will put a link to these slides in the description, and you can go get them for yourselves, and therefore you can get all of these links. But this link is to show you in this blog Azure Databricks documentation. You do need to have premium if you want to use your data catalog, and of course for Delta Live tables, same thing. So now we're going to get into the real meat of this discussion, which is cluster architecture. But before I get into that, I found this great video, and I'm borrowing from this wherever I can, by Daniel Tomes, I believe is the right way to say that, hopefully. This is about 4 years old, but as far as I can see, almost all of it, if not all of it, is still applicable. Great video, much more digging into the weeds and going into the Spark UI and finding ways to improve the performance of poorly performing workloads. We will get into that as well. I'm backing up a little bit, and I want to create a sort of a broader set of videos that kind of end-to-end cover what to do to get good performance workloads, part of which is fixing ones like Daniel talks about, fixing ones that are not performing well. But as I mentioned, the best place to start is with the right resources being allocated. I will put this link to his video in the description again. Highly recommend you watch it. It's really like the best video I've seen out there, just talking about how to optimize workloads. And he does a really great sort of no-nonsense explanation, which I really appreciate. So let's talk about the cluster architecture. And I've used this diagram in my previous video, but I want to get more into the details now. It all starts with, we'll say Debbie here, who's going to query information against a phone book, which is in storage. And I want to call attention to the fact that we have external storage. So we have to consider the performance of our external storage. But Debbie here writes a query: select city and count from phone book, group by city, order by city. And what's going to happen is that query will go into the driver node. A node in Databricks or Spark is a virtual machine. Can be a physical machine, but who uses real machines anymore? So it's a virtual machine, and it can have any number of core, but you'll notice also the core are connected to disks, maybe multiple, to read and write. And it also has, memory and other things. So it's a virtual machine with a lot of resources, and that of course will affect performance. The driver node coordinates all of the work going on. In other words, it's going to take Debbie's query here, and it's going to execute it, and it's going to partition the data as needed, distribute it over the cluster nodes, and then have them all start executing in parallel. Now the core we'll talk a little bit more about, but a core can support a single executor or a single task or a single partition, however you want to call it, at a time. And so the number of core determines the level of parallelism you get. A lot of stuff in here. A lot of places where this can get kind of bottlenecked, right? Any kind of physical reads and writes will bottleneck. Network issues can bottleneck you. So there's a lot of things to consider. That sends a result back, and I forgot to mention I added this in after the fact, but RAM is also important, right? How much memory do you have? So the constraints I've talked about in the past is the hardware resources, the software resources, environment, yada yada, and we're going to get down to some more of those, but the focal point really here is hardware resources. And that does also touch on the Databricks runtime as well in versions, but the main focus here is what are we giving it for resources? This is sort of a deeper dive picture of the cluster architecture, just showing two worker nodes, emphasizing in the middle you can see here there's network traffic. That's going to affect your speed, right, if it's slow. You can see our core, and notice something a little more detailed here is our worker VM or node has two core just like before, but the memory is split. Some memory is used for storing things like caching data that you need to hold on to, and another part of the memory is used for actually working and doing your work. And when it runs out of memory, it will write to disk. It's called spilling, and it typically will do that when there's a shuffle. What's a shuffle, Brian? Glad you asked. A shuffle is when you ask it to do something that forces Databricks or Spark to rearrange the data to accomplish your task. That pretty much happens when you do things like joins, because now it needs to co-locate the two different tables you're joining, and it needs to co-locate the keys and related data. So it will move all the data around. It's a very costly operation, as they say, because it's a lot of work for it to move all this data from one node to the other. And oftentimes when it does that, it may need to temporarily write some things to disk in the process. Shuffles are really costly. Other things that can cause shuffles are aggregations. When you do group buys, order buys, and things, it needs to, again, move the data around. So shuffles is something you can't avoid, but you do have to be very mindful of when you're doing any kind of coding on Apache Spark. All right, so we have our worker nodes, and then you see the driver node, and that is also constrained by how much memory it has, how much is split between storage and working, and also disk. So it's also got the same kind of constraints. And of course, our external storage is something to be considering too, because external storage could be like Azure Data Lake Gen 2, which is a really good way to go if you're using Azure. But the faster it can be if it's an SSD versus something like HDD, you're going to get faster responses the faster it can read and write to disk. It is an age-old axiom that any reading and writing to physical hardware is slow. Writing to disk has always been a bottleneck in any kind of data-centric operations. So to review this, we have worker sizes, right? Worker size and CPU type. We're going to go into more details about that. What does that mean? But you actually have some control over the type of CPU you pick, and also how much memory and how many core they have. The memory usage and allocation is something that by default you won't control, but you can do things to tweak that and maximize some optimization when you're running your actual jobs. The local disk speed, as I mentioned, so these disks that are being written to, makes a big difference. How fast is it? Driver configuration, like the Databricks runtime, will make a big difference as well, and how you configure the driver itself. And finally, external disks, as I mentioned, you want to make sure those external disks are obviously in the same region, and in Azure I don't think you can not have them in the same region, but also you have to consider any way you can get it to be as fast as possible is obviously ideal. Another thing to consider, which may seem a little unintuitive, is number of nodes, and that generally it's better to go with larger machines and less nodes than lots of smaller machines. Why is that, Brian? Why wouldn't I want just 1,000 nodes? Well, the deal is this. They have to communicate, right? A cluster all works together, and when you do a shuffle, for instance, which is when it's going to need those nodes, it's going to have to start sending data from one virtual machine to another. And when it does that, it's going to take a lot of network traffic. So having these separate machines means it's going to do a lot of work, and that creates sort of a bottleneck the more it has to keep moving data between your virtual machines. So minimizing the number of nodes is probably a good idea, and I've seen recommendations on Databricks blogs and things to that effect. So let's talk a little bit more about the hardware, starting with CPU and memory. You have CPU and GPU types, and which one you will use depends on what workload you're doing, right? If you're doing your typical data transformation and movement types of things, then you'll probably stick with CPU. If you have heavy duty machine learning going on, good chance you want to go with a GPU, because GPUs are optimized for heavy duty mathematical calculations, which is exactly what you do in machine learning. What about the number of cores, Brian? Well, to summarize this again, a core equals an executor equals a task equals a partition. So in other words, it's going to tell you what degree of parallelism you can get. So it's a really important item, and you generally don't want to leave core wasted too. You've got 300 core out there, but you're only using 5. Not a good idea. And sometimes, as the video I mentioned explains, people do that and end up not leveraging all of the core they could be. Let's talk about memory. You need enough memory to support your workload, and it's pretty easy not to get that. I'm not going to get into all the details here about how the memory is used, but in storage. But if it's storing a lot in caching and holding a lot in memory, and then you're also doing a lot of crunching within that memory, then you can run out, and then you'll hit with spills and potentially even crash the cluster. So you want to make sure you get that right. You want to avoid spills. That's always a good idea. And of course, like I mentioned, you're going to be splitting between working and storage memory. Input and output, network. There's a few things about networks. Not all of this you can really control, but it's good to be aware of. Latency is a big one, right? Local storage versus cross-regional storage, which I don't think you could do with Azure anyway, but maybe the other clouds you could, versus on-prem, which is also going to require, on-prem resources sending into Azure. It's going to add overhead and latency issues. The bandwidth, how fast is all of the hardware? Of course, the weakest link anywhere in there is going to slow things down. And if you're using external resources like Cosmos DB, Azure SQL, Synapse, or any of those things, then you need to consider the latency those particular services have inherently. Now, Cosmos DB is supposed to be super low latency, so you should get really good response. Azure SQL may not be as good that way, and it generally is going to kind of be, by default, more single-threaded. There's techniques you can use to get parallelism even in the retrieval of data out of things like Azure SQL. You can also try to push down some of your queries so that it filters and does as much work on the Azure SQL side before it sends the data into Databricks. So let's look at storage. So we talked about this, but basically you've got HDD and SSD is going to be faster. You want the fastest storage possible. You want it also locality, right? The closer it can be, the less networking it needs to do, the better. As far as I/O, try to avoid spills. And anytime that Spark has to read and write to disk, sometimes you really need this. You want to write something out, but you have to be mindful of the fact that whenever any system really that's data centric is writing to disk, it slows things down a lot. Another thing to be mindful of is what's the Databricks runtime version you're using. The version often determines what features you can take advantage of. So I believe 9.2 Databricks runtime or higher is required to use Photon. We'll talk about Photon, but it's a very highly optimized super way to get fast execution. So you need to have a certain runtime version for that. And other things will also be affected. So optimizing cluster configuration. So this screen shows you the Azure Databricks workspace. And I went to the compute screen, and within that I said I want to create a new cluster. And this is the screen you get. Now I am going to walk through this, so fear not, and we'll cover all of these options. This screen is an extraction and summarization of the blog link you see at the bottom of the screen. But based on the use case or workload type, Azure Databricks recommends the type of compute you should create. So starting with analysis, which is generally going to be interactive development, they recommend using a single node with high memory and a lot of core. Why is that, Brian? Why would you do that? Because you're probably not doing, petabytes of data processing if you're in real time, and if you can avoid a lot of work going between the nodes, probably a good idea, especially since when you're doing analysis, you're probably doing lots of joins, lots of aggregations, and so requiring these shuffles is going to slow things down, cost you more money. So I think that's the reasoning behind that. It may be that you need to go to multiple nodes, but I think this is a pretty good idea because you can pick some pretty large VMs behind a node and work with that. They point out here too, you're likely going to be reading the same data repeatedly, so the node types are storage optimized and disk cache enabled. In other words, that's what they recommend. What about basic ETL? And the way it's defined there is whether or not you have wide transformation. What's a wide transformation? Honestly, I don't like that term because I don't think it means much, but basically it means this. Do you need a shuffle? That's it. A narrow transformation does not require a shuffle. It doesn't require a sort or grouping or join. That's the basic bottom line. So an ETL job that does not have a requirement for a shuffle, no wide transformations, should use compute optimized. If you have more complex, meaning you're requiring shuffles like you're doing a join, then you use compute optimized but with less nodes. And as I said before, the reason for less nodes is that when it does the shuffle, it has less machines to have to pass data around to, which should improve performance and save you some money. Machine learning training, experimentation, and development, they recommend a single node type with high memory and core, which is the same as for analysis. When you're doing machine learning in production, again, minimal working nodes, storage optimized with disk caching enabled, or maybe you're going to want to use GPU. GPU core are great, but I called this out of the notes just to be aware it lacks support for disk caching, which could also impact performance. A couple of options too, which are not really directly related to performance, but good to know since we're covering creating clusters, is you can save a lot of money if you use something called spot instances. What's a spot instance? A spot instance is really like, think of it like the bargain basement. You got this room and it's just got stuff in it, and it's like Microsoft is saying, well, if you grab one of those off that shelf over there, we don't have to do anything for you, then we'll give you a deal. You can see under recommendation, I took that part of the cluster definition screen so you could see that it's just a checkbox. You want to use spot instances. I don't believe spot instances support the same SLAs as non-spot instances, and they're probably not best suited for critical production workloads. But wherever you can use them and you can sort of accept not as much reliability and guaranteed delivery of the virtual machine, you can save some money on it. So that's a good reason to use it. The next thing to consider is serverless compute. This is a very hot topic these days in Databricks. And the nice thing about serverless compute is it's like having clusters just sitting, waiting to be used, but you're not paying for them. That's kind of the idea. Think of cars in a parking lot all warmed up, and all you got to just say, I need one, I need two, and they're ready to go. Now, Databricks is actually the one running those and holding on to them for you, not really Azure specifically. They're there on standby and you can grab them. Databricks does not charge you for that, at least their documentation says that, but there may be some cost through Azure. So why would I use serverless compute, Brian? Save time. Not so much performance, but you got to wait for those clusters to start up. And sometimes you don't want to, right? They can take up to 5 to 7 minutes to bring a cluster up. And let's say it's just a 10-minute job. So you waited 7 minutes, we'll say, and then you wait 10 minutes for the job to run, and then the cluster disappears. With serverless compute, you get nearly instantaneous clusters available to you. And finally, an option which I mentioned is Photon. That's just a checkbox on the screen. We'll see that in a minute, but it provides vastly faster processing. What does Photon do, Brian? Photon is really a rewrite of the Spark engine. That's how I see it. It's like they started out with Spark and they said, we're going to use Scala. We're going to use Scala, and that means we're going to use the Java virtual machine, and they built it all out, and it's great, and it scales really well. And of course, Java is very powerful. It's a really great language for writing stuff that you can control like this. But once you start really wanting to get fast speed, Java wasn't designed to be like machine learning speed. The fastest reasonable language to use would be something like C, and that's exactly what Photon is. So Photon blows past all of the issues and limitations that go with using JVMs on the cluster nodes, and instead replaces most, but not all at this point, with C code, C developed libraries. The cool thing is it still works within the Scala API. In other words, the cluster doesn't really know it's using Photon in a sense. It's sort of masked over it. And the reason for that is so that they can sort of gradually replace parts of the engine without breaking things. At least that's my understanding of how this is working and why. So you want to start replacing things. You want to get that super high powered engine, but you don't want to break everybody's workloads in the meantime. And you certainly don't want to force people to rewrite the code. So the idea with Photon is you don't rewrite it, and Photon will use its enhanced super fast libraries when it can. And when it can't, it will just go back to the regular Scala. But it's not relying on the JVM nearly as much as it used to, and it's orders of magnitude faster. So let's talk a little bit about access mode, because another thing that really doesn't come up all that much. But the first thing to realize is you can do, and I'm kind of skipping the multi-node versus single node. Multi-node is going to be your production workloads mainly, where you have a lot of data and you need to have multiple nodes. So you have to pick one or the other, which you like, multi-node or single node. But you also have this idea of access mode, right? So we see access mode where I've highlighted with the red square. And in my case, it would have your account. So my bkafke at yada, yada, yada. When I pick single user, I have the option, you can see below under advanced options, you have to expand this tab below so you can see the options within it. But one of them is a checkbox to enable credential pass-through for user level data access. What that means is if I have blob storage or ADLS Gen 2 storage, or I have some other resources I need to connect and use from my Databricks workspace, I can authenticate to that resource by having Databricks automatically pass my credentials through. So it knows who I am and says, oh, I know Brian, you're allowed to use this. And that's really convenient when you're doing things, especially more in like development mode, right? You're in a developer workspace, you're trying to get some things working, and you don't have to go and grab Azure Key Vault keys and play with all these different settings and use secret scopes. You can just pass your credentials directly through and get things that you need. And it is primarily, I think, more of a development phase type of feature. One of the things to mention though is because it is a single user, meaning if you want to have a multi-user node, you cannot use pass-through because it doesn't know who it is to pass. In this case, it's just me. It knows I'm the only one using this cluster. And again, a single user node is pretty common for development purposes because then I can spin up my clusters and tear them down and I don't affect other people. But sometimes people want to share a cluster. If you do shared with isolation, I believe is the second one, that keeps everybody nicely organized and separate, but it's limited to using Python and SQL. And if you do the third option, and I'm talking like about here, the no isolation shared supports all languages. We mentioned before, this is the cluster creation screen. You can see the checkbox for use Photon acceleration. Check that off, and you'll notice that in the runtime summary at the right corner, it adds the word Photon. There's not a lot of reasons I can think of not to just check it off and use it, unless you're like me trying to get something to crash for a demo purpose. I would say just usually turn it on and use it and play with it because it's really cool and it's just amazingly powerful how fast it makes things run. Let's talk about the worker types. Here you can see this is a standard, very vanilla kind of VM, and the DS3 I believe maps to the types of VMs that Microsoft offers, so it's kind of a size and capability of the VM. And you can see here 14 gigabyte of memory, total memory for that VM, and 4 core. I believe that's the lowest, cheapest VM you can get and not the most powerful for you doing a workload. You can also set what's called auto scaling, and you do that, you can see at the bottom here, right underneath the driver type, enable auto scaling. When you do that, you set the min workers and max workers. The min workers is what it will automatically start when it creates the cluster. It says, okay, you got 2, for instance, in this case. And if the workload demands more resources, it will keep adding nodes until it reaches the maximum, in this case, 8 nodes. So it's kind of just this range. What's good about doing that, Brian? Money. It saves you money. If you can get by and it only needs 2 nodes, then it won't create more and you don't pay for more. But if it starts to need more nodes available, then it will add them in. It will use them for the duration of the load in which it needs it. And then once the need for them goes away, it will eventually realize I don't need this after a timeout period or something. It will figure out I don't need this anymore, and it will scale the workers down again. So that's why it's a really good idea. If you're going to do multi-nodes, I think using the enable auto scaling is a good feature to use in many cases. And that was the worker types. The driver, you always have only one driver, so we have to create also a VM to be the driver. You can see that it automatically has the same type as the worker. That's the default. There are actually good reasons why you may want to make the driver bigger than the worker nodes. If you're going to be doing a lot of like non-scaled out code, for instance, you're using Python libraries without finding the equivalent Spark version. If you're crunching through a lot of data, you want to do a lot of collects back to the driver. Maybe you're doing a lot of JSON where you're exploding things and bringing it local and doing a lot of that stuff. Maybe you're doing some sort of iteration that's just a local function, training local models. All good reasons why you might want to have a stronger, more powerful driver. And by the way, when you see this LTS next to things, it means long-term support. The general rule of thumb is that production workloads should use the latest LTS when you're creating it new. And if you're doing development, Databricks recommends using actually the latest versions so that you'll be testing out your code against what will become eventually the next LTS. So you don't want to test it against an old LTS and find out that something you're doing, won't work in a future release. At least that's my understanding of why they say that. We can see this slide about getting started with Photon, and the main takeaway here is it has to use Databricks Runtime 9.1 LTS or above. Also, not all instant types of driver and worker nodes are supported with Photon. Photon is available only on Databricks. In other words, if you're using open source Spark, you will not have Photon. Hopefully, they will eventually migrate it there. Another thing I want to call out is when you're creating your nodes, you have the option of picking Delta Cache Accelerated. This has been renamed to Disk Cache, but the bottom line with this is by using this, it automatically caches data that it feels is appropriate, and this improves reading of Parquet files, which means Delta files as well. So if you have Delta tables, data lakehouse, and things going on, then having Delta Cache Accelerated will help you. And the nice thing is you don't have to specify when to cache things. It will do it automatically. You always have the option, with or without that turned on, to cache things you want to in code. So let's take a look at the runtime that we want to pick for our load. The standard is on the left, and you can see it's kind of like a folder structure right here, standard versus ML. Standard would be your typical ETL, ELT types of workloads, and the ML obviously supporting machine learning. The biggest thing I noticed between these two is that when you go to the machine learning side, you have the GPU option, which is highly efficient, expensive, mind you. GPUs are not cheap, but they will give you really fast processing for your machine learning training. You can also notice next to it when you pick a Databricks Runtime which version of Scala and Spark you'll be getting. And that can make a big difference too. Remember I mentioned what can I do in terms of performance? Well, it might be here they all say Spark 3.5. Well, let's say Spark 4.0 has all these cool optimization and enhancement features for performance. You're not going to be able to take advantage of those. So there is a trade-off there. And once you pick it and it's running in say production, you're probably going to be careful about swapping it out. You'll have to test things carefully. So picking the worker type here, you can see this is like the lowest end possible, standard DS3 V2. That's typically what I start with because I'm playing around in development mode to start with. Delta Cache enabled. But if you look down at the bottom, you can see the options here, 16 gig all the way up to 192 gigabyte of memory, 4 core versus 48. So just in that small range, and there's many, you have a lot of options as to how powerful your node is, and that makes a big difference in terms of how much it can achieve parallelism, how much work it can do. Larger nodes mean less nodes required. The driver, as I mentioned, you may want to go with bigger ones. You can see there's lots of options as well here. And again, I mentioned this, make this larger if you want to do more local work without having to sort of scale out in your cluster. I'm going to show you this in a minute, but under advanced options, you can set Spark configurations, many of which can help you optimize your workloads. You can see here like max partition bytes is being set as a sort of hidden example. They just kind of dummied it in there. But these are the kinds of things you could do to improve performance. I'm not going to be talking about that specifically here, but if you need to do things like that, you can do it that way, and then it's automatically, when the cluster boots, it will apply those selections. All right, finally, yay, we're getting to cluster shuffles and spills. Now, I'm showing this because I had to fudge Databricks to create a spill. I actually took what I thought was a fair amount of memory, and no matter what I did, it wouldn't spill. And that's kudos to Databricks. Darn that Photon, does not want to spill data, seems to get through anything. And of course, you also have adaptive query execution, which means when it sees it's running into a problem, it figures it out and fixes it before it runs it. So I had to force this, or I'd be spending a fortune trying to trigger a spill. What I did is, in the Spark config, as I had mentioned, I just set the option spark.executed.memory 1 gig. Now my machine had 14 gig. This brought it down to 1, and I was able to force a spill. Now, in order to see the spill, and this is the whole point of this, you need to go into the Spark UI, and it will show you that it's spilling data. So I ran this query, and I couldn't fit all of it on the screen. So the first cell above is I created a data frame by calling out to Spark SQL, and of course I want to trigger a shuffle. So I'm using the built-in data set, TPCH, and I'm joining line items to orders to customer. I'm doing a group by. I'm doing a left joins because left joins are far more overhead typically than inner joins. So I'm doing that, and then that's returning a Spark data frame. And as you know, if I don't do anything after that, Spark actually won't execute it. It just says, yeah, I'm ready to go when you are. You need to force it to retrieve data. So the second cell over on the right, where it says Python, display SPDF sales, when I do that, it's basically doing some sort of a collect. It has to execute code. It's an action. It will run my job. Now, here's where it shows me, if I go into this expand under it, you'll see the Spark jobs this query is creating. You can see it's doing a lot of different work here, lots of jobs and stages. What we can do is click on the view link to drill into this. Now, in my case, I wasn't sure where it might spill, so I had to poke around a little bit, and I'll show you how I figured out where it's spilling. So when I get into one of the jobs, I just took a look and said, okay, in this case, job 21, I scroll down to the area below here. You see pool name, stage ID, pool name, description, and I clicked on this meaningless name, $sign thread captured, but that showed me what's behind it, and I knew to look at that because I can see on the right side shuffle read, shuffle write. That's what told me, maybe it's spilled here. It's 150.2 megabytes read and 81.8 written. So let's see what it shows us. And the main point here is it shows me that spill memory is 816 megabytes. Spill disk is 75.3 megabytes. So it had to write to disk, and it had to use some extra memory for spilling. Spills generally will degrade performance. It won't necessarily cause real issues. Like in this case, it's still small enough that it was able to easily handle it. But it's something to keep an eye on. And I believe when you start to see spills, it's a good time to consider increasing the memory available and the nodes you're using so that it can do more without spilling. That should help in many cases improve performance. And by the way, notice it says in the blue squares below here, AQE, shuffle read. All that AQE means adaptive query execution. And so that's where it's actually analyzing and redoing its own plan to get the optimal outcome. Pretty cool. So wrapping up, we've talked about why compute resources matter, and I hope that's been made clear. This is the foundation upon which everything is resting. So of course you've got to get it right, and you have lots of options. It's easy to adjust it, but you need to monitor that and make sure it is right. We talked about standard or premium, and honestly, I'll shortcut it to just go with premium. We discussed Databricks and Apache Spark cluster architecture. We had that neat diagram with Debbie submitting the query and kicking off the cluster and all that good stuff. And then we looked sort of at all of the hardware under that and how it affects the performance of your work. Then I walked through optimizing step by step different parts of creating your cluster and the options you pick to make it optimal for your workload. Then I did a little bit of a deep dive on shuffles and spills, because shuffles are really probably the most intense part of Spark work, meaning it will be most likely the thing that causes you the most performance issues, and therefore you want to look at that. And spills, because spills are when shuffles are not able to do all of the work easily, so they have to spill some data, and anytime you're writing to physical hardware like disks, it's going to slow things down. And that's it for this time. I want to thank you for watching. Please like, share, subscribe, and until next time, I'm pulling for you. We're all in this together. Thank you.